Hello and welcome to today's session. This session focuses on learning outcome 2 LO2. Understand the principles underlying neural network training. In this video, we will explore how neural networks learn to perform complex tasks. You will discover the principles of neural network training, from their biological inspiration to practical implementation, and understand how these systems adjust internal parameters to achieve accurate and reliable outcomes. Neural networks draw inspiration from the human brain. They mimic how biological neurons transmit signals. Artificial neurons perform weighted sums followed by activation functions. This mathematical abstraction makes them computationally efficient. Despite the inspiration, they are grounded in mathematical operations. A neural network is organized into layers: input, hidden, and output. Each layer's neurons connect to the next by weighted links. During forward propagation, data moves through these layers. Each neuron computes a weighted sum of inputs. Activation functions then produce outputs. Neural networks act as universal function approximators. Given enough neurons and layers, they can approximate almost any continuous function. This capability explains their power in modeling complex relationships. Backpropagation makes this practical by guiding parameter adjustments. It ensures the network approximates target functions accurately. Forward propagation involves passing input data through the network. Each layer processes data to produce an output. The output layer provides the network's final prediction. This prediction is compared to the correct answer using a loss function. The loss function measures how far the prediction is from the desired goal. Backpropagation is crucial for training neural networks. It propagates error backwards through the network. Gradients indicate how each weight and bias should be adjusted. An optimization algorithm then updates parameters. This process improves network performance over iterations. Activation functions introduce nonlinearity to neural networks. ReLU is simple and efficient, preventing vanishing gradients. PreLU improves flexibility with a learnable gradient for negative inputs. Sigmoid compresses outputs for probability representation. TON helps with data centering and faster convergence. Neural network operations rely on matrix vector multiplications. Each layer's computations are expressed as matrix operations. This allows efficient evaluation using graphics processing units. GPUs are optimized for parallel numerical computation. They are essential for training large neural networks. The bias-variance trade-off is a central challenge in machine learning. Bias refers to error from overly strong assumptions. Variance is error from sensitivity to training data. Reducing bias often increases variance, and vice versa. The goal is to minimize generalization error for reliable performance. Loss functions define the objective for neural network training. They measure how far predictions are from true values. Backpropagation uses loss functions to calculate gradients. Different tasks require different loss functions. Choosing the right loss function is crucial for effective training. Optimization strategies decide how parameter updates are applied. Gradient descent uses the entire dataset for updates. Stochastic gradient descent uses mini-batches for efficiency. Learning rate is critical for training stability. Advanced algorithms like ATOM adapt learning rates dynamically. RMSprop adjusts learning rates based on gradient magnitudes. ATOM combines momentum and adaptive rates for fast convergence. These optimizers outperform plain SGD in early training. They require minimal tuning and are widely used. Understanding these strategies enhances training performance. Several techniques improve training performance. Dropout reduces overfitting by disabling neurons randomly. Learning rate schedulers adjust rates over time. Early stopping prevents overfitting by halting training early. Batch normalization stabilizes learning for faster convergence. Loss functions define what the network aims to minimize. Mean-squared error is used for regression tasks. Cross-entropy loss suits classification tasks. The loss function's shape affects gradient behavior. It directly influences convergence, speed, and training stability. Deep networks have many layers, offering high learning power. Shallow networks are simpler with fewer layers. Deep architectures learn hierarchical representations. Shallow networks are faster to train and easier to interpret. The choice depends on task complexity and data availability. Deep networks excel in learning hierarchical data representations. They handle complex tasks like image recognition. Deeper layers capture intricate patterns efficiently. This makes them suitable for data-intensive problems. Their expressive power surpasses shallow networks. Deep networks require more computational resources. Training takes longer and needs larger datasets. They are prone to overfitting and difficult to interpret. Vanishing gradients pose challenges during training. These factors limit their use in simpler problems. Shallow networks are faster to train and easier to understand. They need fewer parameters and computational power, suitable for smaller datasets and real-time tasks. Perform well on simple problems with lower complexity. Easier to tune and less prone to instability. Shallow networks have limited representational capacity. They struggle with complex hierarchical patterns. Extensive feature engineering is often required. Large numbers of neurons may be needed for complex functions. They lack the expressive strength for intricate tasks. The trade-off between deep and shallow networks involves complexity. Deep networks offer superior performance on complex tasks. They require more data and expertise. Shallow networks provide efficiency and simplicity. Choosing the right architecture depends on task and resources. In conclusion, achieving desired outcomes relies on making informed and well-considered decisions. If you have any questions, simply WhatsApp us at 074843616888. Our team will gladly provide support. Thank you, and see you in the next session.